Phoenix Audio presents
A Brief History of Time by Stephen Hawking. The introduction written by Dr. Carl Sagan. We go about our daily lives understanding almost nothing of the world. We give little thought to the machinery that generates the sunlight that makes life possible, to the gravity that glues us to an Earth that would otherwise send us spinning off into space, or to the atoms of which we're made and on whose stability we fundamentally depend. Except for children who don't know enough not to ask the important questions, few of us spend much time wondering why nature is the way it is, where the cosmos came from, or whether it was always there. If time will one day flow backward, and effects precede causes, or whether there are ultimate limits to what humans can know. There are even children, and I have met some of them, who want to know what a black hole looks like, what is the smallest piece of matter, why we remember the past and not the future, how it is, if there was chaos early, that there is apparently order today, and why there is a universe. In our society, it is still customary for parents and teachers to answer most of these questions with a shrug or with an appeal to vaguely recalled religious precepts. Some are uncomfortable with issues like these because they so vividly expose the limitations of human understanding. But much of philosophy and science has been driven by such inquiries. An increasing number of adults are willing to ask questions of this sort, and occasionally they get some astonishing answers. Equidistant from the atoms and the stars, we are expanding our exploratory horizons to embrace both the very small and the very large. In the spring of 1974, about 2 years before the Viking spacecraft landed on Mars, I was at a meeting in England sponsored by the Royal Society of London to explore the question of how to search for extraterrestrial life. During a coffee break, I noticed that a much larger meeting was being held in an adjacent hall, which, out of curiosity, I entered. I soon realized that I was witnessing an ancient rite, the investiture of new fellows into the Royal Society, one of the most ancient scholarly organizations on the planet. In the front row, a young man in a wheelchair was very slowly signing his name in a book that bore on its earliest pages the signature of Isaac Newton. When at last he finished, there was a stirring ovation. Stephen Hawking was a legend even then. Hawking is now the Lucasian Professor of Mathematics at Cambridge University, a post once held by Newton and later by P.A.M. Dirac, two celebrated explorers of the very large and the very small. He is their worthy successor. This, Hawking's first book for the non-specialist, holds rewards of many kinds for the lay audience. As interesting as the book's wide-ranging contents is the glimpse it provides into the workings of the author's mind. In this book are lucid revelations on the frontiers of physics, astronomy, cosmology, and courage. This is also a book about God, or perhaps about the absence of God. The word God fills these pages. Hawking embarks on a quest to answer Einstein's famous question about whether God had any choice in creating the universe. Hawking is attempting, as he explicitly states, to understand the mind of God. And this makes all the more unexpected the conclusion of the effort, at least so far. A universe with no edge in space, no beginning or end in time, and nothing for a creator to do. Carl Sagan, Cornell University, Ithaca, New York. Chapter 1. Our Picture of the Universe. A well-known scientist, some say it was Bertrand Russell, once gave a public lecture on astronomy. He described how the Earth orbits around the Sun, and how the Sun, in turn, orbits around the center of a vast collection of stars called our galaxy. At the end of the lecture, a little old lady at the back of the room got up and said, "What you've told us is rubbish. The world is really a flat plate supported on the back of a giant tortoise." The scientist gave a superior smile before replying, "What is the tortoise standing on?" "You're very clever, young man, very clever. But it's turtles all the way down." Most people would find the picture of our universe as an infinite tower of tortoises rather ridiculous. But why do we think we know better? What do we know about the universe, and how do we know it? Where did the universe come from? And where's it going? Did the universe have a beginning? And if so, what happened before then? What is the nature of time? Will it ever come to an end? Recent breakthroughs in physics, made possible in part by fantastic new technologies, suggest answers to some of these long-standing questions. Someday these answers may seem as obvious to us on Earth as the Earth is orbiting the Sun, or perhaps as ridiculous as a tower of tortoises. Only time, whatever that may be, will tell. As long ago as 340 BC, the Greek philosopher Aristotle, in his book On the Heavens, was able to put forward two good arguments for believing that the Earth was a round sphere rather than a flat plate. First, he realized that eclipses of the moon were caused by the Earth coming between the Sun and the moon. The Earth's shadow on the moon was always round, which would be true only if the Earth was spherical. If the Earth had been a flat disk, the shadow would have been elongated and elliptical, unless the eclipse always occurred at a time when the Sun was directly under the center of the disk. Second, the Greeks knew from their travels that the North Star appeared lower in the sky when viewed in the south than it did in more northerly regions. Since the North Star lies over the North Pole, it appears to be directly above an observer at the North Pole, but to someone looking from the equator, it appears to lie just at the horizon. From the difference in the apparent position of the North Star in Egypt and Greece, Aristotle even quoted an estimate that the distance around the Earth was 400,000 stadia. It's not known exactly what length a stadium was, but it may have been about 200 yards, which would make Aristotle's estimate about twice the currently accepted figure. The Greeks even had a third argument, that the Earth must be round, for why else does one first see the sails of a ship coming over the horizon and only later see the hull? Aristotle thought that the Earth was stationary and that the Sun, the Moon, the planets, and the stars moved in circular orbits about the Earth. He believed this because he felt, for mystical reasons, that the Earth was the center of the universe, and that circular motion was the most perfect. This idea was elaborated by Ptolemy in the 2nd century AD in a complete cosmological model. The Earth stood at the center, surrounded by 8 spheres that carried the Moon, the Sun, the stars, and the 5 planets known at the time, Mercury, Venus, Mars, Jupiter, and Saturn. The planets themselves moved on smaller circles attached to their respective spheres in order to account for their rather complicated observed paths in the sky. The outermost sphere carried the so-called fixed stars, which always stay in the same position relative to each other, but which rotate together across the sky. What lay beyond the last sphere was never made very clear, but it certainly was not part of mankind's observable universe. Ptolemy's model provided a reasonably accurate system for predicting the positions of heavenly bodies in the sky. But in order to predict these positions correctly, Ptolemy had to make an assumption that the moon followed a path that sometimes brought it twice as close to the Earth as at other times. And that meant that the moon ought sometimes to appear twice as big as at other times. Ptolemy recognized this flaw, but nevertheless his model was generally, although not universally, accepted. It was adopted by the Christian Church as the picture of the universe that was in accordance with Scripture, for it had the great advantage that it left lots of room outside the sphere of fixed stars for heaven and hell. A simpler model was proposed in the year 1514 by a Polish priest, Nicholas Copernicus. At first, perhaps for fear of being branded a heretic by his church, Copernicus circulated his model anonymously. His idea was that the Sun was stationary at the center and that the Earth and the planets moved in circular orbits around the Sun. Nearly a century passed before this idea was taken seriously. Then 2 astronomers, the German Johannes Kepler and the Italian Galileo Galilei, started publicly to support the Copernican theory, despite the fact that the orbits it predicted did not quite match the ones observed. The death blow to the Aristotelian Ptolemaic theory came in 1609. In that year, Galileo started observing the night sky with a telescope, which had just been invented. When he looked at the planet Jupiter, Galileo found that it was accompanied by several small satellites or moons that orbited around it. This implied that everything did not have to orbit directly around the Earth, as Aristotle and Ptolemy had thought. It was, of course, still possible to believe that the Earth was stationary at the center of the universe, and that the moons of Jupiter moved on extremely complicated paths around the Earth, giving the appearance that they orbited Jupiter. However, Copernicus's theory was much simpler. At the same time, Johannes Kepler had modified Copernicus's theory, suggesting that the planets moved not in circles, but in ellipses. An ellipse is an elongated circle. The predictions now finally matched the observations. As far as Kepler was concerned, elliptical orbits were merely an ad hoc hypothesis, and a rather repugnant one at that, because ellipses were clearly less perfect than circles. Having discovered almost by accident that elliptical orbits fit the observations well, he could not reconcile them with his idea that the planets were made to orbit the Sun by magnetic forces. An explanation was provided only much later, in 1687, when Sir Isaac Newton published his Philosophiae Naturalis Principia Mathematica, probably the most important single work ever published in the physical sciences. In it, Newton not only put forward a theory of how bodies move in space and time, but he also developed the complicated mathematics needed to analyze the motions. In addition, Newton postulated a law of universal gravitation, according to which each body in the universe was attracted toward every other body by a force that was stronger and more massive the bodies and the closer they were to each other. It was this same force that caused objects to fall to the ground. The story that Newton was inspired by an apple hitting his head is almost certainly apocryphal. All Newton himself ever said was that the idea of gravity came to him as he sat in contemplative mood, and was occasioned by the fall of an apple. Newton went on to show that according to his law, gravity causes the moon to move in an elliptical orbit around the Earth, and causes the Earth and the planets to follow elliptical paths around the Sun. The Copernican model got rid of Ptolemy's celestial spheres, and with them the idea that the universe had a natural boundary. Since fixed stars did not appear to change their positions apart from a rotation across the sky caused by the Earth spinning on its axis, it became natural to suppose that the fixed stars were objects like our Sun, but very much farther away. Newton realized that according to his theory of gravity, the stars should attract each other, so it seemed that they could not remain essentially motionless. Would they not fall all together at some point? In a letter in 1691 to Richard Bentley, another leading thinker of his day, Newton argued that this would indeed happen if there were only a finite number of stars distributed over a finite region of space. But he reasoned that if, on the other hand, there were an infinite number of stars distributed more or less uniformly over infinite space, this would not happen because there would not be any central point for them to fall to. This argument is an instance of the pitfalls that you can encounter in talking about infinity. In an infinite universe, every point can be regarded as the center, because every point has an infinite number of stars on each side of it. The correct approach, it was realized only much later, is to consider the finite situation, in which the stars all fall in on each other, and then to ask how things change if one adds more stars roughly uniformly distributed outside this region. According to Newton's law, the extra stars would make no difference at all to the original ones on average, so the stars would fall in just as fast. We can add as many stars as we like, but they will always still collapse in on themselves. We now know it is impossible to have an infinite static model of the universe in which gravity is always attractive. It's an interesting reflection on the general climate of thought before the 20th century that no one had suggested that the universe was expanding or contracting. It was generally accepted that either the universe had existed forever in an unchanging state, or that it had been created at a finite time in the past, more or less as we observe it today. In part, this may have been due to people's tendency to believe in eternal truths. as well as the comfort they found in the thought that even though they may grow old and die,